Swayam Prabha. Digital India. Educated India.
Hello everyone. In this class, we will continue our discussion on rings and ideals. We have seen in the last class a very important result called ring homomorphism theorem, which says that if we have a ring homomorphism from one ring R1 to another ring R2, it is called the ring homomorphism F, then we can think of F in two steps. One, first there is a canonical homomorphism to the quotient ring R1 by kernel of F, and then there is a injective ring homomorphism which we call F bar. This is injective. If F is onto ring homomorphism or surjective ring homomorphism, then this becomes an isomorphism. Otherwise, this is an isomorphism, this F bar is an isomorphism of R1 by kernel F with the image of F. So, this F bar is an isomorphism from R1 by kernel F to image of F. This defines an isomorphism. So, this is injective, this part of the map is injective, and the phi kernel F, the canonical homomorphism, the first part is surjective. So, this F map can be broken into these two parts. The first one is surjective, the next one is injective. Now, intuitively what we see that what this is saying is that if we have this ring R1 and this ring R2 and there is this kernel of F which goes to the 0 element, then we also know that every coset of the kernel goes to another element, full coset goes to one element, another coset goes to another element, and so on. So, all these cosets of kernel F get mapped to single elements in the image. So, we are visualizing this map in two steps. First, we are saying let us merge these kernel F and its cosets and imagine them as individual elements in a ring. We construct the quotient ring R1 by kernel F. So, this is R1 by kernel F, where all these kernel F and its cosets are elements. Cosets are the elements, and then every coset is mapped to a single element here. So, if this is the kernel F, it goes to this map, and similarly the other cosets go to other elements here. So, this map is basically merging the cosets to view them as elements in this ring, new ring. So, the quotient ring. So, now in this way of seeing, one can easily verify that if you take any ideal in R 1 here, any ideal here like this which contains kernel F, this ideal which contains kernel F, then this gets mapped to an ideal here, okay, and vice versa. Any ideal in the image, a subring in the subring, the inverse image is an ideal which contains kernel F. So, what we are saying is that take any ideal I of R 1 such that kernel F is contained in I, then F of I is the set of, so if you take A, F of A, where A in I, right. This is an ideal of image F. And similarly, if we take any ideal J of image F, remember image F is a subring of R 2 because F is a ring homomorphism. So, we take any ideal J of that, then the inverse image F inverse J, set of all elements whose image under F is in J, that is the definition of F inverse J. This is an ideal of R 1 and I is contained in it. Okay. So, what this is saying, these two facts together are saying is that there is a one-to-one correspondence between ideals of, so this is kernel, ideals of R 1 which contain kernel F like these, there are many ideals which contain kernel F is this part in the center. There is a one-to-one correspondence between such ideals and the ideals of R 2. 0 element corresponds to kernel F and we have ideals of, all ideals contain the 0 element. So, there is a one-to-one correspondence, this corresponds to this ideal, this corresponds to this ideal and so on. Now, what we are saying here in terms of kernel F also applies in general for any ideal I of R 1. So, if you take any ideal I of R, there is a one-to-one correspondence between ideals containing I and ideals of R 1 by I. Okay, there are ideals like this is the 0 element in the center, all ideals contain the 0 element, there is a one-to-one correspondence between the ideals like this. Now, this is a very insightful visualization. Okay. Now, let us prove this simple lemma, which is that suppose F is a commutative ring with identity, then F is a field if it has no ideal other than the the trivial ideals 0 and f. Let us prove it. So, first the forward direction. If f is a field, we will show that there is no ideal other than 0 and f. So, take any ideal, let I be an ideal which is non-zero, which means that there is a non-zero element in I. Suppose A is in I, A not equal to 0. Then consider the ideal generated by A. Okay, because f is a field, we see that there is an element A inverse. Okay, A is non-zero element, so it has an inverse in the field. So, what will be this A, the ideal generated by A? It will contain 1, okay, since A inverse is there in F. Okay, A inverse when multiplied with A will be 1 itself, but this also means that this ideal generated by A is same as F. Okay, because with 1 you can multiply all the elements and you will get all the elements of F. So, what you see that any non-zero ideal basically is F. So, there is no other element ideal than 0 and F. Now, the opposite direction, suppose there is no ideal other than 0 and F, then we will show that F is a field. So, we take A, any element A in F, so that A is non-zero, and we want to show that there is a inverse in F, that then we are done, right, because otherwise F is already given to be a commutative ring with identity. So, all we need to show is that A has an inverse if A is non-zero. So, very similar to the first step. So, we just consider the ideal generated by A. Okay. Because A is non-zero, this is not the 0 ideal. So, by the given condition, because these are the only two ideals 0 and F, this must be equal to F then, this equal to F, the full ideal, the ring itself. That means that 1 is there in A, which means there is an element with which you can multiply A to get 1. 1 is equal to AB for some B in F, that is it. So, that B is the inverse. Okay. Now, we will discuss some special types of ideals. One is called maximal ideal. What is a maximal ideal? If you have a commutative ring with identity and you have an ideal, so that there is no ideal in between this ideal and the ring. There is no ideal like this which contains I and which is also not equal to R. So, I is ideal I is called maximal if for any ideal J such that I J R forms a chain, it should be true that either J equal to I or J equal to R. There is no ideal in between, strictly in between. Any ideal in between will be either I or J, R itself. Such an ideal is called a maximal ideal. prime ideal. Now, prime ideal is an ideal which has the property that if A and B are ring elements, if the product A B belongs to I, then either A is in I or B is in I. Okay. Then we say that ideal I is a prime ideal. This should happen for all B, A and B. For this should happen, that if A B is in I, then either A is in I or B is in I. Now, examples, we will consider a single example which works for maximal ideal as well as prime ideal. It is a very simple example. Consider the ring of integers and take any prime number p in Z. Take the ideal generated by, we know that Z is actually a PID, principal ideal domain. So, any ideal is generated by a single element. So, consider one which is generated by a prime number and the ideal generated by this. This is basically the set of all integers which are multiples of the prime number p. Now, one can see that this is a prime ideal, because if A B is a multiple of p, A B belongs to p, means that A B is a multiple of p divides A B. Okay. Then we know that because p is a prime number, this is prime. Because p is a prime number, it must happen that p divides either A or B. So, we know that p divides A or p divides B, which means that either A is in P or B is in P. Then you say that this is a, so this is a prime ideal. Now, it is also true that this is a maximal ideal. Why? Okay. So, we will show that this ideal generated by P is maximal. So, for that we need to show that there is no ideal in between P and Z. Okay. We also know that any ideal in Z is a principal ideal, which means that it is a it is generated by some integer A. Okay. So, if we have something like this, we will show that this A ideal must be either this or Z itself. So, since P is in this ideal, the P integer itself is in this ideal, it means that it is a multiple of A, something like A times B. Okay. But we know that P is a prime number, so it cannot be factored non-trivially. So, only way it can happen is that either A equal to 1 or A equal to P. Now, if A is equal to 1, then this means that this is Z. If A is equal to P, then this means this is equal to P. So, you see that this ideal is either this one or this one, it cannot be in between. Now, there are also some special types of elements that that we will come across in various types, special types of rings. So, an element in a ring is called a unit if it has an inverse, multiplicative inverse. Unit is an element which has inverse. Like if you see the integer ring Z, the only elements which have multiplicative inverse are 1 and minus 1. So, these are the units. There are prime elements. They generalize the concept of prime numbers. We have also seen prime polynomials which cannot be factored. So, that concept is generalized here. So, these are elements such that an element a P which cannot be factored, as a B such that A is so basically does not have any factor other than a unit or an must have. So, first let us consider associate. So, if you have any element A and B such that A can be expressed as some unit times B, then we say that A and B are associates of each other. Note that in that case B is also U inverse times A and U inverse is an unit. So, this is a symmetric relationship. Now, a prime element is an element which cannot have a factor, it does not have any factor other than units or associates. Remember that what we are saying basically is saying that 5 is a prime number because it does not have any factor other than plus 1, minus 1, plus 5 and minus 5. Plus 5 and minus 5 are its associates because you can multiply minus 5 by a unit minus 1 to get 5. Minus 1 is a unit. So, these two are associates. So, those factors do not count and plus 1 and minus 1 are units. So, 5 does not have any factor other than plus 1 minus 1 which are units and plus 5 minus 5 which are associates. So, it is a prime element. Okay. Now, we will discuss some facts about maximal and prime ideals. They are closely related to fields and integral domains, as you will see. So, here is an important result. If we have any commutative ring with identity R, an ideal M is maximal if and only if the quotient ring R by M is a field. Okay. M is maximal is equivalent to saying that R by M is a field. We have seen that a field does not have any non-trivial ideal other than the 0 ideal and the full ring itself. Okay. So, this is a generalization of that. In the case of a field, what it means is that the 0 ideal is maximal. There is no ideal in between. Now, here we are saying for any ring, if M is a maximal ideal, in between there is no other ideal, which means that the quotient ring will not have any non-trivial ideal, and so it is a field. Next one says that if an ideal is prime ideal, that is equivalent to saying the quotient ring is an integral domain. Now, as you can see, every field is an integral domain. So, a maximal ideal is also going to be a prime ideal as a result, okay, because the right hand sides, this upper one implies the lower one. So, here also there are equivalent statements on the left hand side, the upper one will imply the lower one. So, that is what this next statement says, every maximal ideal is prime. Now, the fourth one is particularly relevant for PIDs, principal ideal domains, like integer ring and, as we will later see, also the polynomial rings. which are very important for us. So, for PIDs we know that every ideal is generated by an element. So, take ideals of that kind. So, ideal generated by the element C here, okay, take the quotient ring. This quotient ring is a field, which means that this ideal is maximal, right. This is equivalent to saying C is a prime element. So, for PIDs the quotient ring is a field if and only if the generating element is a prime element. Now, let us prove these statements. The first statement is quite obvious from the structure of ideals that we have discussed before, that that R by M, what does R by M being a field means? This is a field, this implies and implied by that R by M has no ideal other than the zero element, which is the ideal M itself, and R by M, no non-trivial ideal. Now, we have discussed that ideals of R by M have a one-to-one correspondence with ideals of R which contain M. So, what this is saying is that R does not have any ideal, R has no ideal containing the ideal M other than M itself and R itself. In between M and R there is no ideal, okay, because there is a one-to-one correspondence between such ideals containing M and ideals of R by M. So, that is it. So, this proves that so this is basically saying M is maximal. Now, this is the first part. Second part says P is a prime ideal if and only if R by P is an integral domain. So, let us prove the forward part first. P is a prime ideal. We want to show that R by P is an integral domain. So, take any two elements in R by P. So, take A and B in R by P. These are the cosets of P. Now, such that A times B, the product, we want to show that R by P is an integral domain, right. So, this is equal to 0. We want to show that A and either A equal to 0 or B equal to 0. Now, this is same as is the definition is that this product is this. So, this is equal to the 0. What it means is that AB is in P. Okay. Now, if AB is in P, because P is a prime ideal, it is given, the left hand side is given, either A in P or B is in P, and that means that either A bar is equal to 0 or B bar is equal to 0. So, that proves the forward part. The backward part, we want to show that P is a prime ideal. So, that means we want to take AB in P, and we want to show that either A is in P or B is in P. So, you just follow very similar principle. This means that AB, this is equal to 0, which is same as this which is 0, and because r by p is an integral domain that is given in the right hand side, this means either a is equal to 0 or b is equal to 0, and that means a is in P or B is in P. So, that proves it. Now, third part is proved trivially, because as we said, from these equivalences we already know that a field is an integral domain. So, this implies this, and so its their equivalents also follow the same implication. So, that proves the third part. Now, the fourth part, R by C is a field if and only if C is a prime element. So, what we will do is we will take all possible cases of C and we will see under what kind of properties this R by C becomes is a field, and we will see that only if and only if C is a prime element, that R by C will be a field. Okay. So, first of all, C may be a unit. So, we will consider cases on C. Case 1, C is a unit. If C is a unit, we know that this is R, because you can multiply C by something to get 1. So, 1 will be in this ideal, and that means the ideal is the full ring R. And that means that R by C has just one element, R by R, okay? And that is not a field. This is not a field. So, if C is a unit, R by C is not a field. Case 2 is C is not a unit or a prime, in which case we know that C has a non-trivial factor. Okay. It is not a prime number, prime element, which means that C has a non-trivial factorization A B, so that A is not a unit or associate of C. There is such a factor A of C. Now, this implies that C belongs to the ideal generated by A, because C is a multiple of A. Okay. And on the other hand, A does not belong to the ideal generated by C. Why? Because if C was also if A was also a multiple of C, then A and C will be associates of each other. Why? Because if A is in C, what it means is that A is some C times D, okay? But C is also AB, so it means it is ABD. Now, bringing to the same side, we get A times 1 minus BD is 0, but this is a principal ideal domain. In particular, it is an integral domain, which means this will imply 1 minus BD is 0, because A is non-zero. Now, that means BD is equal to 1, that means B is a unit. And that means here A is an associate of C. A is an associate of C, which we said it is not, right? A is not a unit and it is not associate of C. So, this case cannot, so A cannot be in C. So, C must be in A and A is not in C. Now, what does that mean? That means that this ideal A, it contains the ideal generated by C, but it is not equal to C, okay, because A does not belong to C, okay, and so this is not equal, and also this is not in R, because A is not a unit. And what it means is that C is not maximal, is not maximal. There is an ideal in between C and R, and that means R by C is not a field. Okay. Now, the case 3, the only case left. So, A is a unit, C is a unit we have considered, C is not a unit nor a prime we have considered. Now, the only thing that can happen is C is a prime. Now, what if C is a prime? C is prime. We want to show that in that case R by C is a field, which is equivalent to saying that C is maximal, the ideal generated by C is maximal. So, to prove that, let us consider any ideal J such that J contains C. Okay, so, we will show that J will be either C itself or R. Now, because it is a PID, J is generated by a single element. Let us call it A. It is generated by A. Okay. Now, what this means, because C belongs to that ideal generated by A, it means that C is a multiple of A, AB. Now, if C is a prime, it means that A will be either A is a unit or associate of C. If A is a unit, it would mean that that ideal J is R. If it is an associate of C, it would mean that that ideal is same as C. So, this is equal to J, J is same as C. So, J is either A itself or J is either R or C, it cannot be strictly in between. So, that proves that this is maximal, and hence C, hence R by C is a field. Okay, so, this completes the proof of these statements, but the statements themselves are very intuitive. It says that basically M is maximal. There is a nice structure. If M is there is an ideal. If it is a take any ideal I, if it is a maximal ideal, then there is nothing in between here, okay, which then means that in the quotient ring there is no non-trivial ideal, because this I is collapsed into 0 here, single elements in the quotient ring R by I. So, if there is no ideal in between here, then there is no non-trivial ideal here either. So, these are equivalent statements. So, R by and this having no non-trivial ideal is equivalent to saying R by I is a field. Now, on the left hand side, if we say that I is a prime ideal, it means that the quotient ring is an integral domain, and if we are considering PIDs, if this ring is a PID, then every ideal is generated by a single element, and we can say whether that an ideal is a maximal ideal or not by just considering what kind of element that it is generated by. If that element is a prime element, then it is maximal, otherwise not. So, in particular, we now can see as a special case that which a fact that we already know, which is that for the integer ring Z, Z by P is a field if and only if P is prime. And we will also see later that the polynomial ring for any field F polynomial ring X is a PID as well. And hence, you take any polynomial Fx, the quotient ring is a field if Fx is prime. And this will play a very important role in our construction of finite fields. However, we will show later that Fx is a PID. Okay, that is it for now. Thank you.